So today we're going to look at points of concurrency and give you a sense of what a point of concurrency is. I'm going to do a little demonstration in GeoGebra for you. So later on this week, I'm going to give you an opportunity to play around with GeoGebra one more time. And part of what I'm doing today, you're gonna get to do. But I'm going to create a triangle. And I'm going to find or just construct the angle bisector. So here's one of them. But instead of just doing one angle bisector, I'm going to bisect another angle as well. So I'm going to bisect angle C. And we're going to look at the point at where these angle bisectors intersect, or where they cross. That point's going to have a special name. In this case, we call this point the incenter. And if I were to create the third angle bisector, guess where it's going to cross? Also going to cross at point D. To have two lines cross at one point, not so interesting. But to have three different lines cross at the same point, or it is kind of a rarity. It does not happen a lot. And in fact, these are all angle bisectors. And if I were to just reorient this triangle, you can see that those three lines, those three angle bisectors, always stay crossing at that same point. And when you have more than two lines crossing at the same point, we call that point a point of concurrency, which is the title of your notes, points of concurrency. You don't have to remember that, but you do want to remember the name of this point. This point is called the incenter, and I have that defined for you. I'll point that out in a second. So there's so the point where all the angle bisectors cross, we call the incenter, and that incenter has some properties. I'm going to hide my lines, my angle bisectors, and just take a look at that incenter. That incenter, if we look at the distance from that incenter to a side of the triangle, well, first of all, how do you find the distance from a point to a line in general? Like, because where do I go on that line? Like, if I want to go from point D to measure the distance from that point to side AB, I mean, do I go from D to A? Do I go from D to B? Do I go from D to some point in between? How do you find the distance? And the distance is always the shortest distance, because you have lots of points to choose. Which one would give you the shortest distance? Any idea? It's going to be perpendicular. That's the key thing. And I'm going to put a point where that perpendicular crosses. And we can pretty easily show that, hey, you can't beat that distance. That's going to be the shortest distance. If you pick something else, I could show you that's going to be longer. Because then you get this like right triangle, and hypotenuse is always the longest side of that right triangle. And so we can always show that DE is going to be shorter than anything else. So that distance from D to E is the shortest distance from my incenter to that side of the triangle. I'm going to go, well, what if we look at the distance from that to another side of the triangle? So let's say I go from D to this side. Or if I go from D to this side, and I'm going to find those points of intersection. And now we don't need those lines anymore, so I'm going to hide the lines. And this is what it looks like. Okay, so now as I move my triangle around, we could see the incenter, which is D, and we can see kind of where the points would be perpendicular on the side. So if we measured from D to E, or D to F, or D to G, we find the distance from that incenter to any side of that triangle. What do you guys think is going to happen here? Any hypotheses? In terms of the incenter and the distance to each side of the triangle? What's that? Yeah. Probably, it might be the same. So to measure that, I'm gonna take a circle, because a circle has a radius, right, equidistant all the way around. And so if I take that circle to one of the points, you think that circle will also go through the other 2 points? Well, let's check. So if I go to E, then it's also going through F and G. And so it turns out that the incenter is always the same distance to all 3 sides of that triangle. And because of that property, we can circumscribe a circle with a triangle, which is like make that circle stuck inside a triangle no matter how we move it around, which is kind of it's not an easy thing to do if you didn't know how to do that, but the incenter is the key to that. Okay. All right, so enough of GeoGebra. Let's go back here. I gave you 4 new definitions, and we just looked at them right now. We said, hey, if we get all our angle bisectors in a triangle and look at where they cross, they're going to cross at one point, and that point has a special name called the incenter. Well, if we took the time and did the same thing with just perpendicular bisectors, we'd see that they would also cross at one point, and that point would be a different point than the incenter, but it'd still be a point of concurrency, and we call it the circumcenter. If we did the same thing with the medians, we'd see that they all cross at a point, and that's called the centroid, which is this one actually comes up, and it's important in physics because it's the center of mass of the triangle. It's the balancing point. So if you were to draw all 3 medians and see where they cross, and if it were a 3-dimensional equal density type triangle, you could balance it at the centroid. And then lastly, if you had all 3 altitudes, they all cross at what we call the orthocenter. So you have to know these 4 names, those 4 new names: the circumcenter, incenter, centroid, and orthocenter. And you're going to have to know which type of side, or which type of segment or line they go with, so that the circumcenter goes with perpendicular bisector, the incenter goes with angle bisector, centroid goes with medians, orthocenter goes with altitude. You got to know that. And that's the only new thing that we're working with today. Okay. Everything else is kind of in the same style of what we've been doing. So let's do number 1 together. Your homework is going to be to do the 4 problems, but we'll do one. I'll do one with you. Take a minute and work ahead of me on the proof. See if you can start to fill in some reasons. The givens are that E is an incenter of triangle ABC, and that ED is perpendicular to AB, EF is perpendicular to BC, EG is perpendicular to AC. Okay, those are given to us, and then the proof starts at line 2 and says that angle AGE, I'm going to AGE, this angle here, ADE, this angle here, I'll defrost it for you. There we go. All right. Let's see what else. CGE. I'm going to change colors for a reason here. So CGE, this one here, and CFE, that those are all right angles. And we need a reason for that. And that reason has to come from line 1, because there's nothing else in the proof, or it comes directly from the picture. but this one's going to come from line 1. So what's our reason for line 2? Yeah. Definition of perpendicular, right? And in line 1 it says it's perpendicular, so we're able to jump there. All right, then line 3 says that AE bisects BAC and CE bisects angle BCA. Why would that be? Why would AE be an angle bisector and CE be an angle bisector? All right, so this is the new part. Yes, definition of incenter. So this is why you want to know what is an incenter. An incenter is the point where the angle bisectors cross. And well, if an angle what's an angle bisector? Well, that's something that's connected to a vertex, and so therefore everything's fit in the bill here, right? And so they have to be angle bisectors. So that's coming from step 1 as well. So then 4 says that angle GCE, this angle here, is going to match this angle here, and it also says this angle here is going to match this angle here. Why would we say that for step 4? Something that was stated before. Definition of, yeah, angle bisector. Definition of angle bisector. Because in step 3, we said that they're angle bisectors, and this is what it means to be an angle bisector. In step 5, we're now saying we have congruence, that the right angles are congruent to each other. And we know that, but we just want to state why. So what would the reason be for 5? Yeah. All right angles are congruent. Okay. And then step 6 says that AE is congruent to AE. And also EC is congruent to EC. Why would things be congruent to themselves? Reflexive property of congruent. So now you can see what I put in blue, those two triangles are congruent to each other, and what is in green, both those triangles are congruent to each other. Why? Side, 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 angle, side, angle, angle, side, hypotenuse, leg. Angle, angle, side. We had 2 angles and a side in each of those, and that's coming from steps 4, 5, and 6. And now because of that, we can say that, well, this is congruent to this. You know, the distance from E to D is going to be the same distance from E to G. And the distance from E to G is going to be the same distance from E to F. Why? CP, CTC. Corresponding parts of congruent triangles are congruent. And that's from step 7. And therefore, we prove that the incenter is the same distance to all 3 sides. Now let's go to part B. Part B, we want to find the distance from A to E. And so you want to be familiar with that distance formula. And the distance formula is going to say, well, take the x value from A and E and subtract them. So here's the x value from A minus the x value from E, and then square that, plus the y value from A is square root of 27, minus the y value from E is the square root of 147. Square that, and then don't forget to take the square root of all of that. That's the distance formula. That's plugging it in, and then we work through these steps. Got my equal sign. So negative root 12 minus 0, that's just negative root 12. Still squared. plus, what is the square root of 27 minus the square root of 147? Actually, we're not allowed to subtract square roots if they're not the same. So you can only add or subtract square roots if they're exactly the same. So what we're stuck here unless we could simplify. So square root of 27, can we break that down to something here? We can actually change it to 3 root 3. And how about 147? Can you come up with a number that goes into 147? 3. And it actually turns out to be 3 times 49. And 49 is 7 times 7. So we're going to get 7 root 3. So before we couldn't subtract, now we can because they're both in that root 3 form. Don't forget that square root. So square root of this, or sorry, the square root of negative 12, or negative square root of 12 squared, negative times negative is positive, and the square and the square root kind of undo each other. So you just get 12 plus, and we could subtract these now, and you just go 3 minus 7, that's a negative 4, square root 3, and we haven't squared it yet, so we still need to put in parentheses with the square, and all this is still underneath the square root sign. See if you could finish that off. So when you square it, you get 12 plus negative 4 squared is positive 16, and you're going to multiply that with root 3 times root 3, which is 3. So that comes out to be 12 plus 48, which is the square root of 60. And you can simplify that to 2 root 15. And then now you're going to have to show that EC is the same as that. Okay, I'll let you pick up from there. Homework is to finish 1, 2, 3, and 4, okay?